Imagine a universe frozen in time. Look closely at the space surrounding a stationary electric charge. You'll see a constant, stable field of energy. The moment that charge begins to move, it generates a magnetic field. These concentric rings represent a physical force that only emerges when in motion. In the summer of 1820, Danish physicist Hans Christian Ørsted proved this connection. During a lecture, he noticed that sending an electric current through a straight wire caused a nearby compass needle to deflect. While often studied separately, electricity and magnetism form a single, interconnected system, one activated by velocity. Following Ørsted's discovery, scientists spent decades unifying these two forces. These hidden fields could be mapped, they could be precisely measured, and eventually fully controlled. By 1864, James Clerk Maxwell successfully unified the mathematics of both forces. His equations proved that light is an electromagnetic wave rippling through these fields. Mapping these invisible fields allowed humanity to project information through the air. This understanding directly enabled the telegraph, radio, and all modern wireless communication. To understand how motion creates magnetism, we have to start with the baseline interaction, electrostatics. This follows a strict two-stage process. First, a stationary source charge Q alters the geometry of the space around it, projecting vectors outward in straight lines. This spatial alteration is the electric field, or E. The magnitude of this field depends on the distance r from our source charge. The second stage occurs when a new object enters that space. If we introduce a smaller test charge, Q, it interacts with the pre-existing field and is physically repelled or attracted along those vector lines. This interaction produces a measurable physical force. The force on our test charge is the product of its own charge and the electric field it has entered. In environments with multiple charges, these fields follow the principle of superposition. The individual fields from each source add together vectorially to create a single combined web of force. These fields are physical realities. They carry energy and momentum through space, taking a finite amount of time to propagate from the source to the test charge. What happens to this stationary system when we apply motion? Moving charges generate a secondary structure called the magnetic field, denoted as B. Unlike the straight vectors of an electric field, the magnetic field forms closed circular loops perpendicular to the path of the current. This is also a vector field, defined at every point in space. Its strength and direction depend on the position relative to the moving charge. The principle of superposition applies here as well. When multiple currents flow near each other, their magnetic fields add together to create a single unified field at every point. The SI unit for the magnetic field is the Tesla, named after Nikola Tesla. Velocity is the essential requirement for this force. If the charge is not moving, the magnetic force is zero. Only a moving charge creates a magnetic field, and only a moving charge can actually feel its effects. When both concepts are layered together, we see that a moving charge generates both an electric and a magnetic field simultaneously. Looking at the particle head-on, the geometry is precise. The radiating electric field lines and the circular magnetic loops intersect at a 90-degree angle. This specific overlapping relationship determines the Lorentz force. When a particle enters this space, the total force it experiences is the vector sum of the pushes from both the electric and magnetic fields. These rules define the architecture of our universe. Stationary charges create electric fields, velocity adds magnetic fields, and both are governed by superposition,